on scientific notation. So if you guys remember scientific notation, the whole purpose of scientific notation is to be able to make large numbers small and small numbers large. Okay, so I wanted to talk a little bit about scientific notation real quick here, because this is something that we deal with a lot, and you'll see quite a bit of it in science. So first of all, scientific notation is helpful to take numbers that are really, really big like this, or that are really, really small like this and make them manageable. Right here, this number, 1 mole is equal to 60222 atoms. This is a very large number. This mass right here, this is the mass of a proton, and this is a very, very, very small number, okay? I know that this is a very, very big number because I have a lot of zeros to the right. I know this is a very, very small number because I have a lot of zeros to my left, lots of zeros between what we say a non-zero digit and a decimal point. So this guy up here, this guy is a very big number, and this guy is a very small number. It would be a real pain in the butt to have to deal with numbers so big or so small. So we put it in scientific notation. So scientific notation has a general form, and it looks like this. M times 10 to the some sort of exponent, okay? This M is considered to be kind of our main number. It's always, this number is our main number, if you want to think of it like this. This, whatever number goes into this spot is going to be between 1 and 9.99. And this is going to be our exponent times 10 to the whatever. Now, the thing that you really have to remember is that the number that goes right here in front of the times 10 to the whatever, this has to be between 1 and 9.99. That tells you when you're going to stop moving your decimal. Okay, so in order to take big numbers and put them into scientific notation, you go to the very end of the number and you put an implied decimal. And I'm going to move my decimal over as many times as I have to get a number that's between 1 and 9.99. So I'm going to start moving and I'm going to start counting. So I'm going to move my decimal to the left. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I'm not going to end there because that would be 60, and 23. I'm going to end right there. So my new number is 6.02 times 10, okay? And I move my decimal over 23 places, so that's 10 to the 23rd. Since I am moving my decimal to the left, my exponent is positive. Okay, and whatever units we have out here, I'm going to put on the outside. We don't want to squeeze it in here. We don't want to squeeze it in here. This is my entire number. 6.02 times 10 to the 23rd atoms. That's a lot of atoms. Now we're going to do the same thing with our small number. This time we are going to move our decimal to the right. So this time, instead of, since I'm going in the opposite direction, instead of my exponent being positive, it's going to be negative. So again, I'm going to move my decimal over until I hit a number that's between 1 and 9.99. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I can't end there because that's smaller than 1. 27 is a little bit larger than 1. So my number will be 1.67 times 10 to the negative 21st kilograms. And I think it was 21. I lost count. I forgot. 3, 6, 9, 12, 15, 18, 19, 20, 21, 22, 23, 24, 25, 26. Wow, 27. Just kidding. That's how bad my memory is. Again, unit goes on the outside. Don't squeeze it on there in the inside someplace. And that's a quick reminder of scientific notation because you will have an assignment over that. Okay, you guys, take care. Have a good one.